Hello my dear students, welcome to my YouTube channel that's Concepts of Chemistry. Before starting today's lecture, please do subscribe my channel. My dear students, today we are going to study most important topic of chemistry, that's electronic configuration of elements. Electronic configuration is the distribution of electrons in different shells, subshells, orbitals, but in the increasing order of the energies of shell and subshells, which we have read in the Aufbau principle. So let me write what we are going to do. Electronic configuration. So it is the distribution of electrons in shells, subshells and orbitals. But in the increasing order of energies of shell and the subshell. But in the increasing order of energies of shells and subshells. So let me write the energy order of all subshells up to the 118th element. So that energy order that we have read in the Aufbau principle was the subshell with the minimum energy is 1 cell 1s, then the turn is of 2s, then there is a 2p, then 3s, then 3p, then 4s, then 3d, then 4p, then 5s, then 4d, then 5p, then 6s, then 4f, then 5d, then 6p, then 7s, then 5f, then 6d, and finally 7p. So this is the order of increasing energies of all the subshells. It is increasing order of energies of all subshells. Here you can observe that the minimum energy is of 1s and the maximum energy is of 7p. So we have to fill electrons in these subshells in the order of the increasing energy of subshells. That's called electronic configuration. So let me take an example. As an example, I am taking atomic number 20. As example, we are taking atomic number 20. We have to write the electronic configuration of atomic number 20. That means we have 20 electrons that we have to fill in the various subshells. So before doing that, let us recapitulate one thing. S subshell. S subshell has how many orbitals? 1 orbital. Now 1 orbital can accommodate how many electrons? 2 electrons of opposite spin, that is plus half and the minus half. Now let's talk about the p subshell. That's my p subshell. In p subshell, how many orbitals we are having? It's 3 orbitals. Now one orbital accommodates 2 electrons, then 3 orbitals will accommodate 6 electrons. Now let's talk about d subshell. D subshell have 5 orbitals. So the maximum number of electrons that can be accommodated in 5 orbitals are 10 electrons. Now let's talk about the F subshell. F subshell has 7 orbitals. So 7 orbitals will accommodate maximum of 14 electrons. Now let's come back to the example. We have to fill 20 electrons in the subshells in the increasing order of energies of subshells. So let me write this thing. I'm writing 1s, then I'm writing 2s, then I'm writing 2p, then I'm writing 3s, then 3p, then 4s. Now it's the increasing order of energies of subshell. I have taken that up to only 4s. So now let's fill the electrons. Now the least energy is of 1s, so the firstly electrons will enter in the 1s. Now s has 1 orbital, so it can accommodate only 2 electrons, so s will get 2 electrons. Now we are left with 18. Now the turn is of 2s subshell. Again s subshell will accommodate 2 electrons, so 2 over here. So we are left with now 16 electrons. Now energy wise turn is of 2p. Now p subshell accommodate maximum of 6 electrons. So 6 electrons over here. So we got 10 electrons completed, then 10 electrons are left. Now we will fill the 3s. Now again s subshell will have 2 electrons. Now we are left with 8 electrons. Now 3p. P subshell accommodate maximum of again 6 electrons. So we got total 18 electrons over here. Now 2 are left. The next turn is of 4s. Now s subshell again acquires only 2 electrons. So here we got 20 electrons completed. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2 is the electronic configuration of atomic number 20. That's calcium. So now let's take another example. I'm taking atomic number to be 35. 35 stands for we have to fill 35 electrons in subshells arranged in the increasing order of the energies. Now let me write the increasing order of the energies of subshells. So I'm writing 1s, then the turn is of 2s, then 2p, then 3s, then 3p, then 4s, then 3d, and then 5p. So now let's fill the electrons. As stated, 1s will get the electrons first because of least energy, then 2s, then 2p, and so on. So in 35 electrons, I am filling 2 electrons in the 1s because s subshell has 2 electrons, so I got 2 over here. So it's 1s2. The next turn is of 2s. Again it's an s subshell. We got 2 electrons over here. Now the turn is of 2p. The p acquires maximum of 6 electrons, so we got 6 electrons over here. Up to 2p6 we got complete 10 electrons. So now let's move forward. Now is the turn of 3s. Now 3s will acquire 2 electrons. Then is the turn of 3p. Again p subshell acquires 6 electron. Next return of 4s. Now s subshell acquires only 2 electrons. So here we got 20 electrons completed. So now let's come to 3d. 3d acquires maximum of 10 electrons. So up to 3d we got 30 electrons completed. Now we have to fill 5 more electrons because the atomic number was 35. Now 5p can acquire maximum of 6 electrons, but we are available with only 5 electrons now. So we will write just 5 electrons in 5p, and that's the electronic configuration of atomic number 35. So hopefully you got this point. Now let's move to the next topic. So now I'm talking about the most stable electronic configurations. The electronic configuration in which all orbitals of same subshell are either half filled or completely filled are more stable due to symmetrical distribution of electrons. Consequently, the electrons are more strongly attracted by the nucleus, which brings the stability. So, my next topic was most stable electronic configuration. So, I'm writing most stable electronic configuration. The electronic configuration in which all the orbitals of same subshell, I'm writing the electronic configuration in which all orbitals of same subshell, because they are degenerate orbitals. The electronic configuration in which all orbitals of same subshell are either half filled according to Hund's rule. I am mentioning specifically according to Hund's rule. Is either half filled or completely filled. Are more stable due to the symmetrical distribution of electrons. Are more stable due to symmetrical distribution of electrons. Consequently, they will be attracted more by the nucleus. Attracted more by the nucleus. So now, let me take an example to clear this thing. The stable configurations are of two types, the completely filled and the half filled. I am writing the stable configurations are of two types, completely filled electronic configuration and the another one is half filled electronic configuration. Now let's take the example of completive electronic configuration, and they are noble gases. Very importantly, noble gases. What does the word noble stands for? Noble stands for non-reacting. Why they are non-reacting? Because they are stable. Why they are stable? Because of completely full electronic configuration. So let me take an example. I'm taking the example of neon gas. Neon, the atomic number is 10. That means we have to fill 10 electrons. So I'm writing 1s, 2s, the 2p, the increasing order of energy of subshells. So we have to fill 10 electrons. So 1s will get firstly 2 electrons because of the lowest energy of 1s. Then the turn of 2s, the 2 electrons, and then is the turn of 2p, the 6 electrons. So it's a completely full electronic configuration up to 2p. Up to 2p. So let me talk about the 2p in a little detail. We are talking about the 2p. In p subshell, we always have 3 orbitals, and they are degenerate orbitals. So let me draw these 3 orbitals in the form of boxes. So we got the 3 degenerate orbitals. The first one is 2px, the second one is 2pz, and the third one is 2py. So we have to fill 6 electrons over here. So I will fill the electrons according to the Hund's rule. That is, firstly all the orbitals will get 1 electron each. After that the pairing will start. So I got the first electron in 2px, the second one in 2pz, and the third one is 2py. So we got the 3 electrons, but we have to fill 6. Now the fourth electron will again go in the 2px, but with the opposite spin. Now fifth electron in 2pz, and the sixth electron in 2py. So we got completely filled electronic configuration in the last subshell being filled, and the last subshell was 2p. So we got completely filled electronic configuration in the last subshell, which got filled by the electrons. That's why it's a completely filled electronic configuration. That's why it's a stable one. That's why it's a noble gas. So now let's talk about the half-filled electronic configuration. For half-filled electronic configuration, I'm taking the example of nitrogen. What's the atomic number of nitrogen? It's 7. That means we have to fill 7 electrons. So let me write the configuration: 1s, then 2s, then 2p. It's the increasing order of energies of subshell. So now fill the 7 electrons. Firstly 1s will get 2 electrons, then 2s will get 2 electrons. We have to fill 7, so we are left with 3. So the 2p will get 3 electrons. So now let's talk about 2p in little detail. Again it's a 2p. The 2p will have 3 degenerate orbitals, that is orbitals with equal energies. So let me draw this thing. The first orbital is 2px, the second one is 2pz, and the third one is 2py. So now let's fill 3 electrons according to Hund's rule. So the first electron is in 2px. The second electron will occupy 2pz according to Hund's rule, and then the third one will be in 2py. So we got the 3 electrons in different subshells with the least inter-electronic repulsive forces. That's why it's stable, because of least inter-electronic repulsive forces, as the 3 electrons are in different subshells, in different orbitals of 2p subshell. That's why this is a least electronic repulsions, least inter-electronic repulsions, because the 3 electrons are in different orbitals of 2p subshell. That's why the half-filled electronic configurations are stable. So I hope you got the reason that the 3 electrons are in different orbitals of 2p subshell. So that's why it's a half-filled configuration and it's a stable one. So that's all for today. I hope you all understood today's lecture. You got to know how to make the electronic configurations. In the next chapter of periodicity, I will tell you about the tricks, how to identify the electronic configuration in just a fraction of second. I will tell you about the tricks in the lectures of periodicity. There you will got to know how to evaluate the electronic configuration in just a fraction of seconds. So that's all. I hope you all understood today's lecture. If any student wants to book a paid one-to-one online class to clear their doubts, then she can contact me. My phone number is mentioned on thumbnail of this lecture. Please like, subscribe and share my channel to maximum number of students. Don't forget to press the subscribe button. Stay blessed.